Hello everyone, hope you're doing and welcome back to my channel. Today we're at day 28 of the November daily LeetCode challenge, and we have a hard question in front of us. This is the third hard question that we had in the November daily LeetCode challenge, and as you might be knowing from the last few days, we are having questions on graph. Again, this is a question on graph, and be very proud to know that this is a hard question of graph. And hard, when you are preparing for interviews, you will always get to know that graph is the most hardest topic. So today you are going to solve one of the hardest questions in graph. I will not say this is hard. This is actually easy question. This is just a basic level question to know that that particular algorithm. But yeah, if you know the algorithm, this will not be hard. Only thing is you have to identify whether in this situation that algorithm will work or not. Okay, that is the only hard part. Other than that, implementation part is not at all hard. Okay, if you have been following my videos for the last 3 days, that is whenever we get a graph question, last 3 days I guess. Whenever if you have been following my video, I'm damn sure we'll be able to solve it. Though this is not a simple BFS question, here we'll be using a different algorithm, but still you will be able to do it if you have been following my videos. Okay, the slight difference only, but you will be able to get it. That's that much I'm sure of that. So let's see this question. So yep, let's start. It's question 2290. Minimum obstacle removal to reach corner. Okay, let me first zoom in so that you can get a clear view. I will always give the link of the question in the description. You can always pause the video, check out the question link, and just for your sake, get a nice clarity on the question by yourself. Okay, that is always the best part. Okay, I always prefer you to go through the question and learn. Okay, instead of like seeing the explanation given in my video. Okay, come to this explanation only if you're not stuck somewhere. Okay, that is the expectation. So basically, you are given a zero index to the array. Okay, first see the inputs. You are given a grid basically. Okay, this grid is going to be a binary grid. That is, it will always have zeros and ones. It's a 2D grid. Okay, for example. So what happens is whenever there is a blockage, it will be shown as a one. If it is a clear box, it will be shown as a zero. Okay, that is the idea that following. So you will have to tell us like, okay, let's see the question. We'll get to know. The idea here is we have to reach the last node. That is the bottommost. That is right bottommost node from 0 comma 0. Okay, that is m minus 1 comma n minus 1. You have to reach from 0 comma 0. Okay, that is the task. You are given a zero index 2D array grid of size m into n. Each cell has two values. What are these? Either 0, which represents empty cell, or 1, which represents obstacle that should be removed. Okay, you can move up or down, left or right from and to an empty cell. Okay, as you might be knowing, you can move up and down. You can move in all the four directions basically. If the cell is not empty, you'll have to make it empty to move into that. Okay, as simple as that. Return the minimum number of obstacles to remove so that you can move from the left upper corner, that is 0 comma 0, to the right lower corner, that is m minus 1 comma n minus 1. Okay, so the idea is you can move between empty cells, that is fine. But if a cell is not empty and if you want to move into that, you will have to remove that obstacle. Okay, so that is the basic idea. So you will have to tell me if you have to go from 0 comma 0 to the m minus 1 comma n minus 1, that is the rightmost bottom node. Okay, so you will have to tell what is the minimum number of obstacles that you need to remove. Okay, as simple as that. So that is the question. I hope you get the good clarity of the question. If you have not got the clarity, let us see the example one first. Then I will come to the solution of it. Okay. So if you see in this particular example, so the blocks are shown here. So the idea here is you cannot reach from 0 comma 0 to m minus 1 comma n minus 1 without removing a block. Okay. Do you agree with me? Yes, that is the case. So we'll have to see what is the minimum number of blocks that we need to remove. Okay, as simple as that. So for example, if you see here, if you are basically removing these two blocks. Okay, the 0 comma 1 and 0 comma 2, if you're removing these two blocks, basically it will look something like this. Okay, in the right image of what you are seeing. So if without just by removing two blocks you can reach the destination. Okay, because other cells are anyway empty. Okay, other cells are empty. But if you take any other path, you may get to remove three blocks. But in this case we want only the minimum number of obstacles to be removed. Okay, so that is the solution for example number one. Okay, we'll come to example number two. Example number one is very easy. You can reach 0 comma 0 to m minus 1 comma n minus 1 without removing any blocks. Okay, because there is a path. Okay, you can take that path and you can reach. So if you are seeing this question for the first time, let me tell you that, see, it's how it is different from the previous question. If you have seen my yesterday's question, or day before yesterday's question, what we were doing is, see, there what we dealt with, there were graphs where edges were not having any weights. Okay, if you have to imagine this as a graph, what we will have to do first is, see, this is going to be a graph where the edges are going to have a weight. What is that weight? See, that weight is going to be like this particular. For example, if I have to move from 0 comma 0 to 0 comma 1, I will have to pass that weight. Okay, that is the basic idea. But if I have to move from an empty cell to empty cell, I don't have to pass any weight. So see, that there comes the topic of the shortest path. Okay, there comes the topic of the shortest path. Shortest path is basically where we can reach from the source to target with least, with by taking a path which has the least number of weight. Okay, so here we are going to take these blocks as edges with weight. Okay, and similarly when we move from empty cell to empty cell, those are going to be edges without any weight. Okay, as simple as that. That's what we are going to do in this particular example. Okay, if you see the constraints, they are slightly bigger. Okay, it is 10 power 5 to 10 power 5. So the matrix is going to be really huge. At max it can have 10 power 5 into 10 power 5 elements, which is around 10 power 10 elements, okay, at max. So we have, that is slightly bigger, yeah. So we'll have to use the algorithm which is most efficient to get the answer, okay. So that is the basic idea in this question. So since let me tell you the all the things that are happening, so that you can get a clarity on why we are using this algorithm. See, first thing is, we need an algorithm where we can find the shortest path, and the shortest algorithm should be able to take into consideration the fact that here all the edges are not equal, okay. Here some edges are having a higher weight. That is the first point. Next thing is, here the weight cannot be negative, okay. So the weights cannot be negative. The weights will be any either zero or a positive weight, okay, as simple as that. So the algorithm that we are going to use for this particular scenario will be Dijkstra's algorithm. Okay, so this algorithm is basically for finding the shortest path from one particular source to all other vertices. Okay, from a single source to all other vertices. Okay, so this algorithm is good for that. So we will see the implementation of that. See, it's very simple to implement. Okay, in Q. So basically, if you see in the yesterday's video or previous videos of mine, what I was doing is I was doing a simple BFS. BFS is just a traversal algorithm. Okay, so there we are not considering the weights and all. Okay, there we are assuming that everything is of zero weight only. Okay, that all the edges are having the same weight. That's what we were considering. So whichever node we reach first, that is the answer. That's what we were doing actually. That was BFS. There we are using a simple queue. But here, instead of a queue, we'll have to use a different data structure. We will get to that. It is going to be a min heap. We'll get to that. But yeah, just understand what is Dijkstra's algorithm. It is for the shortest path from one vertex to all other vertices. Okay. So let us start the question first. So I'm just capturing the dimensions of my given matrix. Okay. So then what I'm doing, I'm just okay. Let me zoom in so that you can get a better clarity. Yep. See, I will again come to example one, but just understand the what we're doing. It's very simple to BFS. Only thing is, in place of queue, we are now going to use a heap. Okay, min heap. Remember that. So if you're not aware what a min heap is, please go and do a Google search. You'll get to know. Min heap is the structure in which you will see, if you do a pop in that, you are always going to get the smallest element. Okay, that is the only idea. Remember, it is not sorting the area of any kind. It's not kind of sorting. Okay, at least we are in this case not using to use as in a sorting way. Okay, we just want the smallest element in each case. Remember that. So if you print basically a heap, we'll get to know that it's not sorting the array as such. Okay, only it is ensuring that the smallest element is there in the top. Okay, that is the only purpose of a heap. Okay, it's not sorting something as such. Okay, if you have to sort, you will have to pop each element to sort it. That is a different way, but in this case we're not going to do that. Okay, so I'm just capturing the directions because it's a 2D kind of grid. So there are only four directions, up, down, right, and left. Okay, so I'm just capturing them. So what are the, for example, for a zero, that is for a zero upward movement, there are two possibilities: either I move right or left. Okay, so that is what is captured in this. Just a second. Yeah, for the first two, and the other one is if we don't move any vertical direction, we have only two possibilities: left and right. And similarly, if we don't move in horizontal direction, we have two possibilities: up and down. Okay, so that is what is captured here. Okay, fine. Next, we are going to create a matrix which is going to have same dimension that of the grid. Okay, another matrix. So what is this going to be? Initially, all the elements in this is going to be infinite. Okay, so basically the dimension of grid and the dimension of this particular matrix. Okay, shortest path from source is going to be same. Okay, the dimension are same, but here every element will be having an infinite value initially. Okay, this will tell me, for example, here I go to an index, let us say I comma j. The value of that in this particular matrix is going to tell me what is the shortest path, what is the shortest path to reach to this particular node from my source. Okay, what is the source, what is the minimum path to reach this particular node. Okay, that is what it is going to store. Okay, so yeah, shortest path basically, when I say it, I mean to say that how much weights, that is how many edges and the weights, that is sum of the weights among the edges that we travel to reach this particular part in the shortest way. Okay, so initially all the elements are going to be infinite, as simple as that. Finally, since we are going to start from a particular node that is going to be a source, in this case source is 0 comma 0. Okay, so whatever is the weight of 0 comma 0, that is whatever, for example, it is either 0 or 1, right? So that we are going to transfer it to that particular index 0 comma 0. Okay, this is the one time thing. Okay, so whichever is the source, for that I have to do this. Okay, so grid of 0 comma 0, it will be either 0 or 1. Okay, this particular value, I'm just taking it and storing it here, as simple as that, right? Fine. Then I'm inserting my first element to my min heap. Okay, min heap, if you see initially, this is the first element. Okay, and this is just a simple array for now. But yeah, when we do the insert and that insert part and the removal part, it behaves like a menu after that. Okay, for example, the heap push and the heap pop. Okay, when we do those operations, we are calling through this particular library, and there those cases it is making it behave like a heap. Okay, as simple as that. Fine. So what are the things? So this whole thing is going to be my first element. Okay, what are they? See, the first thing. Okay, in my first element, the first part is going to be the minimum distance to reach x comma y. Okay, in this case, x comma y is the 0 comma 0. Then it is the x and y coordinates. Okay, 0 comma 0. Fine. I'm starting them. Remember, in min heap, always the first element will be taken to sort. Okay, remember that part. Fine. Then I'm calling till my heap has any element. Okay, I'm doing a pop. I'm capturing those things. I do not need this particular value as such. Okay, so I'm just capturing it in this particular element, and the other two are x comma y. Okay, x comma y, x and y. Fine. What I'm doing, I'm going through each of the directions, and I'm going to get the adjacent neighbors of my x comma y. Okay, I'm calling them as double x and double y. Okay, these are going to be my adjacent neighbors in all the four directions. I'm checking whether these x and y are basically in the grid or not. Okay, if they're not in the grid, I'm not doing anything. Okay, if they're in the grid, what I'm doing, I'm just seeing from my current node, that is for my x comma y. Okay, I know the see I have the shortest path for x comma y. Okay, I'm going to take that. So this is going to be the shortest path for x comma y. Okay, that is from 0 comma 0 to reach x comma y. What is the shortest path? I'm going to take that value. I'm going to add the value of grid of x comma y. Okay, remember this is a grid value. That is grid is given to me, right? This is a grid value. That is either it will be 0 or 1. Okay, as the idea is from a current node, I want to reach this node. Okay, grid of x, double x and double y. If I'm checking, I'm just calling it the shortest path. Okay, so from my if the I'm going to trying to reach the double x and double y from this particular node. Okay, x comma y. So this is going to be the path in that case. Okay, I'm just checking whether this path is shorter than the shortest path from source mentioned in this. Initially, remember all the values will be infinite. Okay, so I'm just trying to check whether the this shortest path is going to be really the shortest path we have seen till now for this particular node. If that is the case, I'm going to change that. Okay, I'm just changing the assignment. Okay, I'm removing the previous value and assigning the new value, and then I'm pushing another element to the heap. Okay, what is that element? I'm just pushing the shortest path. Okay, and then double x and double y. Okay, simple as that. This for the neighbor, I'm just making an entry in that. Okay, so whenever we see a shortest, that is whenever we discover a new short path, we are going to make an entry to the heap, as simple as that, right? So this loop will continue ultimately till we are stuck. That is for any new element we are not finding a shortest path. Okay, that is shortest path already exists. Any path that we're finding is no more shortest. So till then it will be called, and when the heap is empty, finally will come out of this particular loop. Once we come out of this loop, what we have to return, we have to return the shortest path from source for the last element, that is the bottommost right value, that is this particular value. Okay, m minus 1 comma n minus 1. Okay, that value. So for that, we'll have to remove the answer. Okay, that is we have to return the value for that particular node. Okay, so see the way that I have called. Okay, it will be n minus 1 comma n minus 1 for me. Okay, as simple as that. So let me quickly run this and show you, and then we will again go to the example 1, example 2. Yeah, so this is currently we are at example 1, right? So if you see the output, this is telling me the shortest path from source for all the values. Okay, so if you see the shortest path from for the 0 comma 0 to itself is 0. Okay, then for the 0 comma 1 is 1, for 0 comma 2 is 2. Why? Because here basically you had these bricks. Okay, that is the reason why. Similarly for these two. Okay, for 1 comma 0 it is 1, for 1 comma 2 it is 2, and so on. Okay, if you see this particular thing, it is 2, that is 3. What is that? It is basically 2 comma 2. Okay, it is 3. Basically, if to reach this particular node, you have to lift 3 blocks. That is the basic idea. But for the last, this is the answer, right? For this, it is 2. Okay, so that is why we are removing 2 as the answer. If you take about the example 2, in example 2, basically we had a simply, we don't have to remove any obstacle. Okay, there is a path. Okay, so we are using that. So if you see here, for that reason, only where those blocks are present, only for those cases we had a 1. Okay, otherwise we will not have 1 in any way. Okay, so here this is going to be our answer, and we are going to, sorry, this is going to be our answer, and we are going to return that. Okay, so yeah, that is the one. So here what we use the Dijkstra's algorithm. Okay. Other thing is, see, the only hard part here is to understand how to apply that Dijkstra's algorithm here. Okay, that is the first part. Okay, if you're not able to understand, see, you can solve this question multiple ways, but this question I felt is more of a application of the algorithm. Okay, so first of all, you have to identify whether this situation is inconvenient for me to apply the Dijkstra algorithm. You have to convert this grid problem to a graph problem, and then you have to solve it using the algorithm. Okay, as simple as that. If you see in this algorithm, we are not making any change. Okay, this is the pure algorithm that we are using. Remember, in harder question, what will happen is we have to make changes to the algorithm, but in this case, we are not doing that. Okay, so we are simply using it as it is. So coming to the space and time complexity of it, if you see, this is the only thing where it is using some space, and obviously this part also. Okay, so if you talk about the space complexity, because of this particular array, which is of the same dimension as that of my grid, so the space complexity of m into n. Okay, of m into n. Now coming to the time complexity, say we are basically using the heap sort. We're doing heap push and heap pop. Okay, so what will happen is, see, what is the maximum number of element that can be there in a heap? First of all, it can be the size of the grid, right? It can be of the size of the grid, which is m into n. Okay, now for m into n, what is happening? If you see, we are either doing a push or a pop. Okay, so basically for this, the space and time considerably of this one. Okay, m into n log m into n. Okay, see, log m into n tells me how much time it will need basically to rearrange the heap when you do a push or a pop. Okay, that is the simple way of thing. Okay, whenever you do a push or a pop, this is the time that is going to need to rearrange the heap. Okay, and at max there are going to m into n elements, so this is going to be this much time, and this will be called at most for m into n times. Okay, as simple as that, in a range of upper limit of m into n. For that reason, the space and time concept is like this. Okay, so yeah, that was all for today. If you have learned anything from this question, please do subscribe to my channel. Really gives a lot of motivation to continue further. I can give this code in this description in the comments. You can try it on your own, right? So yeah, that was all for today. See you tomorrow. Thanks a lot.